we have not been able to attend, and that is the reason for the early deterioration of concrete. One more point I would like to highlight, that the examples I showed you here, they all, when they were constructed, obviously there were several things missing, but as per the codal provisions, whatever requirements were prescribed, they were followed, and the concrete used here actually passed the acceptance criteria. So even after passing the acceptance criteria, they deteriorated at early age. So what the reasons could be? There are few I have listed. There could be more as well. That there could be improper design of the structures. Then you can attribute to bad detailing as well. That happens many times, where the congestion of reinforcement that results in the honeycombing, etc., and finally results in early deterioration. Then poor quality of materials used, maybe the cement, aggregate, and fine aggregate and coarse aggregate. Then some bad construction practices followed, not pouring it properly, the transportation being done badly. There could be several of them, and maybe some accidental loading for which the structure was not designed. And the last one is the aggressive environment. I mention here that aggressive environment for the simple reason that the environment is always attacking the concrete, and there are mechanisms which try deteriorating the concrete. In one are the reinforcement corrosion, try initiating the reinforcement corrosion, which result in deterioration of concrete. So out of the several factors mentioned here, mostly we are able to control the top ones, but we would be actually focusing on the main reason for the deterioration as aggressive environment, which is causing the reinforcement corrosion and resulting in the deterioration of concrete. So some of them I listed here because as I said that today we are going to discuss the importance of the cover zone concrete, and that is the reason I listed these deterioration mechanisms. The chloride ingress, carbonation of concrete, freeze thaw, thermal cracking, shrinkage, and there could be some other mechanism as well. So the chloride ingress is the chloride, if this is a reinforced concrete section, so chlorides attack from the cover zone, they reach to the reinforcement, and the corrosion products are formed, and the cracking occurs in the cover zone. So that means the access to the chloride ions for reaching to the reinforcement becomes easier, and more of them reach, and further the spalling of concrete starts. So we can see that here this area of concrete is mainly responsible for the corrosion of reinforcement, which is a cover of about 40-50 mm, and mainly its permeation properties are responsible for bringing the outside harmful agent to inside the and reaching to the reinforcement and causing the corrosion. So just a diagram showing the corrosion process where the chlorides come, there are anodic and cathodic regions formed, and the corrosion of reinforcement start from the cement matrix. Here the chlorides, carbon dioxide, oxygen and moisture is ingressing inside this and causing the corrosion of reinforcement, and ultimately resulting in cracking, and finally getting the starting the cracking and spalling of concrete. The second the mechanism I mentioned is the carbonation, which is when the cement is hydrating, in addition to the calcium silicate hydrate, this calcium hydroxide forms, which when is attacked by the carbon dioxide from the atmosphere. CaCO3 is there, and this has also a tendency of leaching out. So when it is leaching out, it leaves more pore, and there is a mechanism of the similar type as you saw for the chloride ingress, that carbon dioxide is reaching to the surface of the concrete and trying to carbonate this. So this carbonation is happening layer by layer from the cover, and as the time progresses, more carbon dioxide diffuses in and with the air, and the carbonation front starts to move towards the reinforcement. As long as it is not reaching the reinforcement, the reinforcement is protected, and as it reaches to the reinforcement, a protective passive layer is lost because of the loss of pH, and the corrosion can start. You can see that here the outer phenolphthalein spray test showing that this part is not carbonated, whereas the outside is completely carbonated, and the corrosion has started. This is how do we do phenolphthalein test. We took a sample, and just if you spray phenolphthalein, you are able to gauge that how much carbonation of concrete has happened. So the corrosion process is of slightly different here. The earlier was because of the corrosion. Now here, when the passivity is lost because of the formation of the anodic and cathodic regions, there is some corrosion current, and Fe ion gets released and rest is formed, and this process continues. And as we know, this is a pictorial depiction of the corrosion products formed. You can see that the different forms have different volumes, and the total volume goes quite high, and which is responsible for exerting pressure on the cover zone concrete, which is very thin, and it is unable to sustain, and it starts cracking and spalling starts. Then the freeze thaw effect is also mainly contributed to the cover zone, where because of the water moisture present inside it, when it freezes, exerts pressure on the outer surface and causes some cracks. So more water can be trapped in, and in the next freezing thawing cycle, which are getting repeated, more cracking happens, and ultimately the breaking of concrete or the deterioration of concrete happens in the cover zone, and that is supplemented with the corrosion of reinforcement. So if we just try reviewing it, that few of the deterioration mechanism we just had. So what is mainly responsible? That cover zone permeation properties, which are mainly responsible for bringing the harmful things to inside the concrete and to the reinforcement, and then the reinforcement cover. If the cover is reasonably insufficient, the corrosion could start at an early age. Then the hydration process of cement, because the type of cement we are using, if the hydration is formed, or giving the cement hydration is giving a porous framework, then the permeation properties would be higher, and it will get more permeability, diffusion and absorption kind of thing, and the more and more harmful agents will be able to reach to the reinforcement and cause the deterioration of concrete. Also the environmental factors. So mainly the courts have tried incorporating by taking different types of exposure conditions. In harsher environment, this process may be speed up. So what I'm trying to say that this whole thing is happening through this cover zone, all these deterioration mechanisms. So how do we control these durability parameters? So some of them are listed here, that you can control water cement ratio, cement type and content, total water content of the concrete, use of mineral admixtures, aggregate grading and type, giving proper compaction and curing. So the purpose of all these controlling parameters is to reduce the permeation properties of concrete, where the harmful agencies would not find easy access to enter into the concrete and reach to the reinforcement. So we are taking some of the measures by specifying minimum grade of concrete for different exposure conditions. Minimum cement content should be there from the durability considerations. Nowadays, maximum cement content is also there. Otherwise, there is thermal cracking inside the concrete, which again causes problems for the durability of concrete. Similarly, maximum water cement ratios for different grades, for different exposure conditions, and the use of mineral admixtures like fly ash, silica fume, etc. So some of the measures which are prescribed, but the restrictive measures are there. We are mainly using cube strength as acceptance criteria, and in at least Indian standards, the performance-based specifications not implemented completely, although these days many contracts have started putting their own conditions which are performance based, which is a very good sign, and the quantitative assessment of performance indicators are still not suggested. So this becomes very important that we control the cover zone concrete by applying different methodologies, so that the durability of concrete is achieved. So how do we improve that? As I mentioned in the previous slide, that low water cement ratio ensures that the porosity of concrete is less, and the lesser pores give a more impermeable kind of concrete in the cover zone, and the concrete behavior for long-term durability becomes better. The addition of pozzolanic material, we have been using this and trying to reduce the permeability. Adequate cover, curing, and use of controlled permeability formwork, some surface treatment, and we are using other cementitious materials also. There are several, I think I would not like to discuss today, like geopolymer concrete. There are different MgO based cement. There are different cementitious materials being tried to tackle this problem. So what happens when we are making concrete? So the concrete is normally, when we are talking about it, many times say that it is a three-phase system. One is the coarse aggregate, as you can see here, and the cement matrix. But there is also a region around the aggregate, which is we call interfacial transition zone. So that the properties of if you see that aggregate, the cement paste, and this zone adjacent to concrete or around the aggregate, they have different properties, and that is why these are called three-phase system. And this interfacial transition zone has also a great effect on durability, and especially when it comes to the cover zone properties of concrete. So let's assume that there is an aggregate. This is the cement paste. So it has been observed that if we are unable to control a few parameters, this area, which is shown here in yellow color, which we call interfacial transition zone, that comes out to be more porous as compared to the main matrix. So the attempt has to be that we try controlling for a particular mix the parameters which are able to make this this transition zone more compact and more uniform as the remaining cement matrix. That is going to improve the durability, and these are some of the micrographs of concrete. You can see that here quite dense cement concrete interface is visible, being prepared with the low water cement ratio, whereas the other two examples, you can see that there is a interfacial zone where this black is actually the amount of pores present. So if you have more water coming into the system, and it is not able, it is getting accumulated near the aggregates. So the more porous structure is formed near the aggregate, and that is responsible for increasing its permeability, diffusion and absorption properties of concrete, and which is ultimately resulting in the early deterioration of these structures. We should try improving this, and it has been observed that if we use the silica fume or fly ash, so this calcium hydroxide, which is a byproduct, gets consumed, and CSH is formed. So in a way, it is giving more compact framework of the matrix, and the properties are reasonably improved, and we get better durable concrete. Also, in a reinforced concrete structure, when we are vibrating the concrete, so there is a tendency for water to try expelling towards the outer boundaries. The air being very light comes up, and also some of the water tries flowing here and also towards the outer boundaries. And in the process of vibration, the more water gets accumulated in the outer cover zone, as you can see here. So when you are vibrating, more water goes outside, gets accumulated. So the effective water cement ratio, if we observed, this is popularly depicted something like that the water cement ratio in the outer cover zone becomes quite high as compared to the lower one. So suppose someone used 0.45 water cement ratio, vibrated the concrete. So during the vibration, more water is trapped here in the cover zone. So the effective water cement ratio becomes quite high here, and some of the water is going from this mass core concrete outside, so it might be slightly lesser than what you use because more water is accumulated here. So this, in a small region, being moved water gets a higher water cement ratio, which obviously results in lower quality of our lower compressive strength. And also because of the presence of more water or more water cement ratio, the permeability of this region becomes very high. And that is the reason we normally say that total water content should also be controlled when we are proportioning our mixes rather than just balancing the water cement ratio. So that results in, because this area becomes quite porous, so it results in a bad quality structure where early deterioration is expected. So we need to actually look for these things and try controlling that. You can see that here this cover concrete is going because and corrosion of reinforcement, ultimately reducing the diameter of the reinforcement and reducing the load carrying capacities of these structures. So again, I emphasize that this area need to be looked at, and to reduce that, I'll say these days some of the formwork liners are coming, and which could be taken up for making the cover zone properties better. These liners are in fact placed near the in the inner surface of the formwork. So when you do the vibration, the same process happens. The water tries to expel out to these cover zone concrete, and these are having some very small channels kind of thing, and then a membrane here which allows the water to flow out but will not allow the cement particles to go out. So this liner is, if used, this is one of the mechanisms by which we can reduce the effective water cement ratio being obtained here in the outer cover zone concrete. So what happens that when you vibrate the concrete, the water tries to get accumulated here, and then it flows through this membrane and by gravity drains off. So by this process, you can actually reduce the actual water cement ratio here, and which results in better and compact cover zone concrete. So the effective water cement ratio actually in this zone becomes lesser than the core concrete, and that is resulting in better compact cover zone concrete and resulting in more better durability. Also, these days surface treatments are becoming popular, that we apply some silane base or acrylic based surface treatments. So they are basically plugging the pores in the cover zone concrete. So the access to these chlorides, carbon dioxide, oxygen, moisture, etc. gets greatly reduced, and thereby increasing the durability of concrete. I would suggest that these are not the measures for concrete. The first thing is that we should try making good concrete which are satisfying our requirements, and these methods, like especially the surface treatments being expensive ones, should be employed wherever things are going wrong. So once we say that, suppose a prescription is given for using X grade of concrete, M35 or 40, and if we are able to assess the required permeability for the life of the structure, and that is not being achieved in some cases, let's say, so in those cases we can resort to applying this surface treatments, and can improve the quality of delay the deterioration of concrete, or improve the durability of concrete. So these are some of the things we apply, and then we move on to when I'm saying that we improve the cover zone concrete. So how do we assess that after the construction, how the cover zone concrete has actually been made? And that is why we will discuss just very briefly that some of the assessment methodologies we can employ here for assessing the cover zone concrete. Some of them could be in situ, some of them could be in the laboratory as well. So I'll briefly go through the use of some of the tests like pull-off test, initial surface absorption test, water penetration test, water and air permeability, and an in situ migration test also. Many times I'll discuss that later on. So we move on. The pull-off testing is very simple, and I would say not destructive also. If you are using a surface test, just maybe prepare the surface of the concrete, and a disc is normally attached with the epoxy glue, and the equipment applies a tensile force for the failure, and the pull-off tensile strength is achieved, the calculated. In some cases, we can drill partial core also. So the point of application of the tensile force is defined, and you can calculate the tensile strength of concrete, which actually predicts the real tensile strength of the cover zone concrete, because this test is being performed on the surface. There are some more tests also which are of the type that you insert something and they create a bit more destruction than this test. Although when we are doing this test, we have to be careful, because the surface preparation plays an important role, and the destruction in this case is reasonably smaller. So you can use this pull-off testing apparatus, where this testing is being done by drilling partial cores, the small cores. So those small cores of about 10 to 15 mm depth, they come out, and you can get the pull-off testing of pull-off strength of the concrete in cover zone. This is another initial surface absorption test specified in BS code. This is again a surface test where you can see the surface absorption of the concrete. So this is able to give you a hint on one of the parameters of the permeation properties, that is absorption. So it is applying a water head of 200 mm on concrete surface. So either we can do that on the specially prepared cubes of the same concrete, or this could be deployed at site also, but quite difficult. It's not very easy to deploy at site in all these situations. So this is one where you could get the absorption parameters in 10 minutes, 30 minutes test. But that will give you that how the surface is able to absorb the water. That means there are pores, and it is indicating that how porous the cover zone concrete is. Then this is also a very popular test being deployed because easy to perform, and at site also it is being taken or employed now quite regularly. I have seen at sites many people are keeping in their contract documents that this water penetration test has to be performed alongside the compressive strength test, where we have a cube sample alongside the compressive strength test cubes, a cavity is filled with water, and it is kept under pressure, so water starts penetrating into the cube, and after the complete test time, the cube is split and the depth of water penetration is measured. So although this test is not depicting the actual cover zone properties of the site, because that is a laboratory test which can say in a way whatever mixed design we have done, what would be the properties of the surface concrete if you are preparing in the lab, and expecting the similar is going to be depicted at site. So it is again like we cube test also we do in the laboratory, and expect that the similar kind of strength is going to be achieved at site. So in many contracts we keep the restrictive criteria that the water penetration should not be more than, let's say, 10 mm for the concrete to be accepted. So in several places this is being used as an acceptance criteria as well, which is, if not the exactly an in situ test, but the cover zone concrete, but yes, it says that it gives you an idea of the concrete on the surface. So that is how we can perform this. We fabricated in our lab, and the setup where you could put these cubes under pressure, and the water pressure is maintained before you test. Then we can employ some permeability tests also. Some of the methodologies, there are several tests now developed across the world, and people are using. I'm just discussing one of them, and this air permeability test is basically you have the cavity created on top of the concrete surface. So the equipment is fixed here, which has a cavity, and you apply a pressure here, air pressure here. So when the air pressure is, the air tries to diffuse through the concrete. Obviously these surfaces have to be sealed. So this air which is diffusing through the concrete surface, that means the pressure is going to drop, because the pressure, once the pressure of, let's say, 500 millibar is kept, so and then you leave it, so pressure start to dissipate, which is measured every minute for 15 minutes, and then we plot a graph in log of the pressure and the time, and then you get a curve, and the slope of the curve is taken as the permeability index. So when you are plotting the curve and get the slope of that curve, that is indicating an index. So it is not actually the intrinsic permeability, but it is giving you an index. If the concrete is having more porous structure in the cover zone, so more pressure drop is available, and that is an indicator of the more permeability of concrete. So that is how we can calculate the permeability of concrete, and then we can also calculate the water permeability. The same way you apply, you fill the cavity with water and apply the pressure, which actually tries to push the water into it, and the water going through the concrete is measured every minute, and again a curve is plotted between the water going in and under root of the time, and the slope is now again can be taken as the permeability, water permeability index. So these are the indirect ways of calculating the permeability of concrete. It is not, again I say, it is not an intrinsic permeability of the concrete, because those tests take too long time and normally are not practical at site. So this is one. There are few more methodologies also of the similar type which are being used at several places, where you can get an idea of the permeability in the cover zone of concrete. If we are taking a sample, a disc kind of sample, which is prescribed in the code, and apply the pressure and create an steady state kind of situation, so that takes too long a time, and there are several literature also saying that things are changing. So it is a quicker way of finding an index, if not the same permeability, because it is able to differentiate between the two different concretes which have different permeabilities. So, and also this is able to actually attend to the problem we are facing, that this is attending the water permeability or air permeability of concrete in the cover zone. And this we can apply at in situ also. So as I just said, that this graph is going to give us a permeability index, which we use as a reference indicator for the durability parameter. So the test something like looks like this. As I said, there are some more tests also being developed right now, which are in use using slightly different methodologies. But the idea is that these tests are able to get the permeability of the cover zone of concrete. They are not giving the total concrete permeability, basically an indicator of the cover area of concrete. So this could be this is being done on a sample in the laboratory, but this could be deployed at site also, on any slab or the column surface, and we can have an idea of the permeability of concrete. Similarly, we can deploy an in situ migration test as well, where we create a potential difference for known chloride sample to move through the cover zone concrete, and try getting an idea of the in situ chloride migration resistance. The other test we do, the RCPT, or maybe chloride diffusion cells we use. So there we get an idea, but normally that is not the idea of the concrete diffusivity through the cover zone concrete. It is basically you take a concrete disc. So normally that is from the core of concrete, which sometimes can be giving misleading results from the cover zone and the core concrete. This is another type of test which you can put it on site and get an idea of the chloride migration. So there are some typical results of these pull off and compressive strength. I'm just showing just for giving you a flavor of how they can be calculated, and there is a resemblance of the strength and the permeability properties. Now, which is the most durable one? Obviously, we try keeping it minimum. Now, lots of literature is there. Don't want to go in detail. That what could be the parameters which we will be fixing for acceptance criteria. So these are air and water permeability tests performed on site and in the laboratory, and based on that we can make our own acceptance criteria. So finally, I would conclude by saying that measures to improve cover zone properties should be taken from the very beginning, because there is no substitute to making good concrete. While doing the mixed proportion, we should be keeping this aspect also in mind while getting to a good strength. Obviously, we should be following good construction practices if we want to have a better quality concrete, and would suggest strongly that we should use some performance-based specifications for accepting it, and